Welcome to The Explainer. Today, we're diving into something pretty wild. We are going to uncover the invisible physical rules that literally hold our entire universe together. Think about it. Every single object around you right now is locked in this silent, intense battle against gravity, pressure, and force. And today, we're going to break down exactly how they survive it. Okay, let's start by animating a really simple comparison in your mind. Picture yourself holding a rubber band. You pull it on both ends, and it just effortlessly stretches out, right? Now take that exact same pulling force and imagine applying it to a glass window. It doesn't stretch at all. It shatters instantly. So why does that happen? What is the unseen physical law that dictates two completely, totally opposite reactions? Well, it all comes down to what we like to jokingly call the science of squish. See, there's a fundamental mathematical property governing how every single material on Earth bends, stretches, and snaps. It's basically the invisible limit of the physical world. And honestly, it's the exact reason why massive steel bridges stand tall and why tiny rubber balls bounce. That magical property is known as Young's modulus, and you'll usually see it represented by the letter E or Y. To really get this, imagine compressing a thick, heavy metal spring. You push it down, that's the load, and when you let go, it bounces back perfectly to its original shape. That specific ability to undergo elastic deformation when you compress or stretch it and then snap back to its original form, that is exactly what Young's modulus measures. It's essentially the ultimate scorecard for a solid's stiffness and its resistance to being deformed. Now, the golden rule here is actually surprisingly simple. If a material has a low Young's modulus value, that means it is highly elastic and flexible. It gives you maximum squish. But on the flip side, a high Young's modulus value, that means the material is inelastic. It is rigid, it's stubborn, and it aggressively resists any attempt to change its shape. So you might be wondering, how do we actually calculate this? We do need to talk about the math for a second, but don't worry, we're gonna make this super easy to visualize. The whole concept really just comes down to the relationship between two physical actions, stress and strain. Let's step through this and animate the math in our heads. Step 1. Imagine a hand pushing down hard on a block. That force being applied over a specific area, that is called stress, and scientists use the Greek letter sigma for it. Step 2. Because you push down, the block physically compresses and changes its length. That deformation is called strain, or epsilon. Step 3. To find Young's modulus, our big E, you just calculate the ratio. You literally just divide the stress by the strain. Force over area divided by the change in length over the original length. Simple as that. Now, because we are dealing with immense physical forces here, the resulting numbers can get absolutely massive. The standard base unit is the Pascal. But honestly, to make the numbers even remotely manageable, scientists usually measure in gigapascals, which is what we'll be using heavily today, or megapascals. And if you're using the imperial system, you're going to see pounds per square inch, or even mega PSI. Actually, before we jump into the numbers, we have to take a quick historical detour, because the backstory of how this crucial modulus was discovered, it is basically a scandalous timeline of stolen credit. I mean, this just brilliantly illustrates how messy science can be. Look at this timeline. Way back in 1727, the legendary Swiss scientist Leonhard Euler describes the basic concept. Decades go by, and in 1782, an Italian scientist named Giordano Riccati actually does the hard work. He performs the physical experiments that lead to the modern calculations we use today. But then, in 1807, a British scientist named Thomas Young just swoops in, publishes the calculation in his course of lectures on natural philosophy, and totally walks away with the naming rights. Honestly, it really should be called Riccati's modulus, but changing it now would just cause endless confusion in the physics world. So, Young's modulus it remains. All right, moving past the historical drama, there's a really surprising physical twist to this mass that we absolutely have to address. See, a material's stiffness isn't always identical in every single direction. Sometimes the angle of your attack changes the entire game. Basically, materials fall into two camps. First, you have isotropic materials, like pure metals and ceramics. Their mechanical properties are exactly the same in all directions. It literally doesn't matter where you press them. But then, we have anisotropic materials. I want you to vividly imagine chopping a block of firewood. If you swing your axe down along the vertical grain, the wood splits beautifully, right? But if you try to chop horizontally across the grain, the axe just bounces right off. Because of their internal grain structure, materials like wood, reinforced concrete, and carbon fiber have drastically different Young's modulus values depending entirely on the direction of the force. Okay, now for the really fun part. Let's dive into the ultimate stiffness leaderboard. We are going to climb the scale of extremes, starting from the stretchiest everyday items and building all the way up to the most unyielding, rigidly stubborn substances known to modern science. We're starting way down at the bottom of the chart with the highly elastic materials, the ones that yield super easily to force. Notice how most synthetic fibers have incredibly low values. Rubber is practically nothing, sitting at just 0.01 to 0.1 gigapascals. Teflon comes in slightly stiffer at 0.5, and nylon sits right around 2.0 to 4.0. These are the squishy materials that are designed to just bend to our will. Ramping up the stiffness, we hit the mid-range. These are the everyday materials we use to literally build our physical world. Wood, when you measure it along the grain, sits at about 11 gigapascals. High-strength concrete gives us solid structural integrity at 30, and aluminum jumps up significantly to 69 gigapascals. We are trusting our lives to these exact numbers every single time we step into a skyscraper or board a commercial airplane. All right, now we enter the realm of the heavy hitters. These are the incredibly stiff metals and carbon structures that vigorously fight back against any attempt to stretch or compress them. Steel is massive, sitting at 200 gigapascals. Tungsten doubles that at 410, and diamond, which is famous for its incredible rigidity, skyrockets to somewhere between 1,050 and 1,210 gigapascals. It is just absurdly stiff. But listen, absolutely nothing prepares you for the peak of the leaderboard: 32,100 gigapascals. This belongs to carbene, which is a specific allotrope of carbon. It completely shutters the rest of the scale. I mean, it literally makes diamond look a bit squishy by comparison. It has the absolute highest Young's modulus of anything we know.
Now, as mind-blowing as that is, we do have to remember one quick limitation here. Young's modulus really only describes elasticity along a single axis or line, basically just pushing and pulling in one direction. But, as we know, the real world is messy, and it operates in 3D.
Because of that, scientists have to use other moduli of elasticity to capture the full picture. Let's try to visualize these advanced concepts in action. For the bulk modulus, picture a solid ball being dunked deep underwater, getting crushed by intense pressure evenly from all sides in 3 dimensions. That is volumetric elasticity. For the shear modulus, picture twisting an object with opposing forces, kind of like wringing out a wet towel, to test its rigidity. Young's modulus is just one piece of a much larger puzzle. So as we wrap up this explainer, I really want to leave you with a thought. Take a second and look at the chair you are sitting in right now, or the walls surrounding your room. They aren't just static, boring objects, right? They are literal mathematical equations holding firm against the forces of nature, defined by their Young's modulus. So how does knowing that change the way you view the built world around you? Keep that invisible battle in mind the next time you stretch a rubber band or try to bend a piece of steel. Thanks so much for learning with me today.